And he's now going to tell us how he applied SHAP to time series forecasting.
Hello everyone, and thanks for the kind introduction. My talk is about explainable time series forecasting with a novel method called SHAP former, which stands for Shapley additive explanations using transformers. So the task I work on is multivariate time series forecasting. Here we have an example of the standardized electricity demand of Baden-Württemberg shown for 1 week, and the goal is to train a model which predicts the electricity demand of the following week. And the model is based on the past electricity demand as well as exogenous variables, including 4 calendar variables and 2 weather variables, temperature and precipitation. Now, of course, we aim for an accurate forecast, but ideally we would also want to get an explanation of that forecast. So we might ask, why did the model predict 10 gigawatt electrical load for tomorrow 1 p.m. and expect an answer such as 7 gigawatt is the mean electricity demand, 3 gigawatts were added because it's a work day, 2 gigawatts because it's 1 p.m. and usually the load is high around noon. Last week the load was lower, therefore it's a bit lower, and also it's a mild temperature, so therefore it's a bit lower. Such explanations of machine learning predictions are commonly computed with a method called Shapley additive explanations, or SHAP in short. So here we are given an instance x containing features x1 to xn, and the method assigns a SHAP value phi I to each feature xi, which represents the contribution of the feature xi to the model prediction. The calculation of the SHAP values is based on feature subsets and marginal contributions. So consider a subset of the feature, which we call S, and a feature xi, which is contained in S. Then the marginal contribution of xi is the model prediction on the feature subset S, so the full feature subset, minus the model prediction on the feature subset S without the feature xi. Finally, the SHAP value for xi is a weighted average of these marginal contributions over different feature subsets. Now there are 2 problems or difficulties with SHAP. One is that on the slide before, the model had more than 2,000 inputs, and this makes 2 to the power 2,000 subsets, which we might consider, and obviously we cannot iterate over all of them. And the second problem is that we usually cannot run a machine learning model on a subset of features. So what is done in practice is to sample the features which are not contained in the subset. So we have to sample multiple times, make a model prediction with each of these samples, and then use the mean of these predictions as the estimate for the model prediction on the feature subset. And these 2 problems make SHAP computationally expensive, and I'm going to present 2 solutions to these problems. So the first one is that we do not compute SHAP values for the individual features, but instead for feature groups. So we are interested in how each previous day affected the model prediction. Therefore, we group the past electricity demand into 7 features, feature groups, each containing 24 values. Whereas for the exogenous variables, we make 1 feature group per variable. So that's 7 for the days, 6 for the exogenous variables, makes 13 in total, which makes more than 8,000 subsets, and it's now feasible to iterate over all of them. And second, we get rid of the sampling by using a mechanism called attention manipulation. Attention basically computes a weighted average of vectors v1 to vn, where the weight is determined by the dot product of the vector with some query vector q. Now we can make use of this and manipulate these weights. For example, if v2 represents temperature and we want to drop out temperature because it's not contained in the feature subset, we can set the weight w2 to 0, and then the vector v2 will not influence the output of the attention mechanism. Therefore, the model has no longer access to this information about the temperature. So now we are able to run our model on feature subsets without having to sample. Our model architecture is kind of a standard encoder-decoder transformer shown here on the right-hand side, but with 2 types of attention manipulation mechanisms. Number 1 is masked feature attention, which we use to drop out exogenous features. And number 2 is masked self-attention and masked cross-attention, which we use to drop out the previous days. The training and inference process looks like this. We start on the left-hand side with the multivariate time series, and then we generate masked inputs, so subsets of the feature groups from this multivariate time series. During training, we sample random masked inputs, whereas during inference, where we want to create an explanation, we use all more than 8,000 subsets. And we use SHAP format to make a prediction for each of these masked inputs, and the predictions which will all look slightly different. So the result of the whole algorithm is once the prediction or the forecast for the next week, which is the model output when the model has all information. And additionally, we have these forecasts for the masked inputs, which we can use to compute marginal contributions and then compute SHAP values from it. So the SHAP values, which we get in the end, tell us for each feature group how that feature group contributed to the model prediction, either in the positive direction or in the negative direction, as you can see here in this colored plot. We evaluate the model accuracy, so how good is the forecast, and we compare it with linear regression, XGBoost, and a transformer. And we see that SHAP format gets a similar accuracy or similar error like a transformer, which is always trained on the full information, so it's not using masked inputs. And these two models outperform XGBoost and linear regression. Next, we look at the runtime needed to create an explanation. So we have the SHAP Python package, and there's a permutation explainer included, and we use that on the transformer model. And this permutation explainer treats each of the input values as an individual feature and computes a SHAP value for each of them. Now running that for only one example requires about 4 minutes. Next, we implemented a custom masker, which does the feature grouping, but it still has to sample from background data. And with that, we bring down the runtime to about half a minute for one example. Whereas with SHAP format, where we don't need sampling, we can create one explanation in less than 1 second. From the SHAP values, we can also compute feature importances, and we use synthetic data to validate our method and the feature importances which it returns. So the synthetic data is a large data set with examples containing different types of seasonalities, a daily seasonality, a weekly seasonality, and a yearly seasonality, as well as dependencies on exogenous data. And since we have access to the data generation process, we can use it to generate ground truth SHAP values. And from these values, compute feature importances. So in this graph, the red lines are the ground truth or expected feature importances, whereas the bars are the feature importances which SHAP format returns. And we see the result is not perfect, but usually the feature importance returned by SHAP format is similar to the ground truth, maybe except for the month feature, which is underestimated by SHAP format. And we have a use case on real empirical data, the electricity demand of Baden-Württemberg. And here we don't have a ground truth available, but we can tell what are the most important features according to SHAP format. And the most important features are the load of the past week, the day of the week, and the hour of the day. A little bit less important is month, holiday, and temperature, and the least important feature is precipitation. Then we can analyze which patterns were learned by the model by looking at dependency plots. Here, each dot represents one explanation of one forecast. On the x-axis, we see the feature values. On the y-axis, we see the associated SHAP values. And on the left-hand plot, we see, for example, that on Saturday and Sunday, the model predicts a lower load than during workdays. In the center, we see the pattern for the hour of the day, and it follows kind of a usual electricity demand curve with low values at night, a peak around noon, and a second peak in the afternoon. Looking at the temperature on the right-hand side, and here only looking at the red dots, which are values during the day, we see when it has less than 15 degrees during the day, people start using electric heating, and therefore the model predicts an increased electricity demand. To conclude, we presented SHAP Former, which is a sampling-free implementation of SHAP based on attention manipulation. It has high accuracy, fast inference. We were able to create an explanation in less than a second, and we validated it on synthetic data. Our key trick was to train the model on feature subsets so that we are, during inference, able to also run the model on feature subsets without having to sample from background data. And I believe that this is also applicable to other models, not only to transformers, so maybe you want to adopt it with your favorite machine learning model in the future. Last but not least, if you're interested in using SHAP Former, then please contact me so that we can stay in touch, and I will notify you when the code is available. With that, I thank you for your hopefully unmanipulated attention, and I'm happy to answer any questions.
Thank you, Matthias. Any questions from the audience? So I have a question. If I were to apply this, I mean, you've already mentioned you will soon release this as a package, maybe, yeah? But if I were to apply this to other time series and other domains, what would be the steps required from me? So the understanding of the variables, modeling them, what is necessary as further parameters?
I mean, you have to collect the data and the exogenous variables which you want to use, and then you would need to define the feature groups you're interested in. I mean, you can do the same that I did, splitting your target variable into days or whatever is interesting for you. If you predict months, then you would, I don't know, group it into years or something like that, and use this like one feature group per exogenous variable, then you would get a similar result as I did. If you have a lot more feature groups than I did, it might no longer be feasible to iterate over all feature group subsets, but you can do something similar like the permutation explainer, which only runs on a subset of these feature groups, and then it would be even faster.
Yeah, thanks for the talk. I have a question related to the attention manipulator that you have mentioned. If, for example, if you change the weight of any of the feature, and if it is a part of any feature subgroup, so will it also affect that feature importance of that subgroup as a result, or?
I manipulate all inputs which belong to one feature subgroup or one feature group together. Okay. So I drop out an entire feature subgroup, a feature group by setting all the weights for these inputs to 0. And that should affect the prediction, and from the difference of this prediction with the prediction where this information is available, I compute the marginal contributions.
That's perfect. Okay, thank you so much.
You're welcome.
All right, let's thank the speaker again.
Thank you.